Hello, and welcome to this recorded learning titled 7 Series Clocking Resources, Part 1. My name is Frank Nelson. I'll be your instructor for this module. This module introduces the clock generation capabilities of the 7 Series FPGAs, including its clock routing resources and clock management resources. After completing this module, you'll be able to describe the clocking resources available in the 7 Series FPGAs, explain the contents of the clock management tile, and be able to add these resources to your design. So we've segmented the contents of the clocking resources into 4 different recordings because the bottom line is the features are extensive and have quite a bit of technical detail to them. So first we're going to start with an overview now, and then we'll get into talking about the clock networks and the clock buffers that are available to our users. In other recordings, we'll talk about the clock management tile, the usage models, as well as show you how to get a hold of these resources and add them to your design. Many systems need extremely high performance clock signals as well as multiple clock domains across a wide range of frequencies. Clocks with related frequencies need to be de-skewed for optimum system performance. Low jitter is also required to maintain the widest possible data window, and double data rate applications will require a precise 50-50 duty cycle to obtain maximum performance. Now, all these requirements must be met with the lowest possible system power consumption, which is quite a challenge for any designer. Xilinx FPGAs have a rich mixture of clocking resources to accommodate these system requirements, offering a good balance of resources at the right cost. As mentioned earlier, most systems require multiple clock frequencies, usually generated from a single clock source. This reduces your system cost and helps ensure that the clocks have a known frequency and a known phase relationship. External clock sources can often be noisy due to board level effects. This issue is resolved by filtering the clock inside the FPGA with dedicated logic resources. This effectively widens the data valid window for the user. External clock and data signals also need to be de-skewed or aligned in order to eliminate hold time issues and race conditions. The clock management tile components in Xilinx FPGAs provide the frequency synthesis, clock filtering, and clock de-skewing functions that designers need. The 7 Series has 3 different clock routing resources: global for your highest fan-out clocks, low skew for regional clocking, and I/O clock routing for SerDes resources. Now we'll talk about the specifics of these clock resources later on in the recordings and explain when you want to use each of these resources. The clock region structures are still important with the 7 Series family of devices. Note that the clock regions now contain 50 CLB rows, not 40 as they did with Vertex 6. The 7 Series FPGAs also have clock management tiles called CMTs, which include PLLs and other clocking resources. Now the 7 Series, like Vertex 6, does not contain a digital clock management resource. That's a DCM. DCM behaviors are now completed in the 7 Series by the use of PLLs. The CMTs perform frequency synthesis, clock de-skew, and jitter filtering. The CMTs accept a very high input frequency range from 10 to 800 MHz. Now this is a very wide range and allows very flexible frequency synthesis. Likewise, the VCO frequency, which is required for the PLLs, has also been improved. It can operate at up to 1.6 GHz. Now all these clocking resources can be easily customized with the use of the Clocking Wizard utility. Now let's have a look at some of the details of the clock networks and the clock buffers that are available to our customers. First, we need to know how external clock signals get into the FPGA. Well, all Xilinx FPGAs have clock-capable input pins. These are regular I/O pins in all respects, but they also have dedicated connections to the internal clocking resources, that being the clock management tiles. Now, if they're not used as clock inputs, they behave like any other I/O pins and can be used for whatever purpose. Each 7 Series device has 4 clock-capable input pins per bank. Each can be single-ended or paired together to form a differential clock input. Thus, each bank can have 4 single-ended or 4 differential clock inputs. Now, we recommend that you refer to the datasheet in the pinout descriptions for details on the number and locations of the clock-capable input pins for your specific device and package combination. You should also note that 2 of the clock-capable input pins are designed as multi-regional clock-capable input pins, and the other two can only be used in a single region. An FPGA is a large array of resources, and many of these resources require clock signals. For any synchronous design to operate properly, clocks must be distributed to use elements with low skew to minimize internal hold time problems. High-performance systems also require low clock jitter. Too much clock jitter reduces the valid data window, increasing the chance of setup and hold time violations. Duty cycle preservation is important for double data rate applications which use both edges of the clock signal. A 50-50 duty cycle is ideal because it gives the rising and falling edge data the same timing characteristics. This minimizes the clock insertion delay and is important for I/O interfaces, since an I/O interface has data signals that travel directly between the external board and the I/O block inside the FPGA. The clock signal must also first be driven through a clock buffer onto a clock routing network. Any discrepancy between the clock and data delays can impact the maximum performance of the interface. Thus, we see there is a lot of challenge in building an optimal clock network for your FPGA design. In this representation of an FPGA die, the blue area represents your CLB logic. The red columns represent the IOBs, that's your I/O pins. The green columns represent clock management tiles, that's your MMCMs and PLLs. And finally, the pink column represents your serial gigabit transceivers. Now, one of the most significant differences with the 7 series is that the CMTs, the clock management tile column, is placed next to the I/O columns. Recall in Vertex 6, they used to be placed in the center of the die. Now, this assures a minimum routing delay which is necessary to assure optimum I/O performance for serial gigabit transceivers as well as SerDes functionality. Now, like Vertex 6, the clock regions are organized into rectangles that are divided by the gray column near the middle of the FPGA. This central gray column represents the global buffers and provides access to the global routing resources. In this example, the black lines, which are located at the bottom of the diagram, help you understand how a clock region is assigned. Each has a central gray line that splits the region horizontally. This is the narrow line towards the middle. This is so an equal number of CLBs are placed above and below the horizontal routing, commonly called the H rows, and as I mentioned, shown as that thinner gray line. Each H row has a fixed number of BUFH buffers, and depending on your device density, you'll have a precise number of fixed clock regions on your die. This is because as the device density increases within a single device subfamily, the die has added additional clock regions to the top of the die. So literally the device gets taller, not wider. The global clock buffers, that's the BUFGs, are in the middle of the device. These drive the vertical spines of the global clock network, which connect to the horizontal spines of the global clock network which run through the middle of each clock region. The horizontal spines are driven by the BUFH buffers. Now, there are also regional clock routing resources called BUFRs. In addition to clocking elements in a single clock region, a BUFR can also drive clocks into some of the neighboring clock regions, but usually, again, only specifically to a region above or below. The BUFIO I/O buffers are placed within the I/O column and are designed to drive the I/O clock network just in that bank. Now, some BUFIOs are capable of spanning multiple clock regions. Each device has 2 I/O columns, one on the left edge and one on the right edge of the die. You should also note that the I/O pins associated with each clock region are placed in a single bank associated only with that clock region. There are also a number of BUFMRs that are dedicated buffers that allow clock inputs to drive the BUFIOs as well as the BUFRs of adjacent clock regions. This is a close-up view of the 7 series of FPGA clock regions. Now, each clock region is 50 CLB rows high and half the width of the device. Unlike earlier FPGAs, there is only one IOB column per clock region. This simplifies the clock networks that are required to actually lay out your design in the device. Now, each clock region contains 12 BUFH buffers that distribute your high fan-out clock signals. Each clock region has 4 regional clock networks called BUFRs, and each clock region also has 4 I/O clock networks per I/O column. The 7 series has a large global clock network that provides for the distribution for up to 32 different global clock signals across the entire FPGA. These reside in the center of the device. The 32 BUFGs each drive one vertical spine of the global clock routing resources. The output of each BUFG can drive onto a BUFH to get to a CLB. Now the routing of the clocks is handled by the tools, so don't get preoccupied by these details. Now please note that when I say a BUFG, I really mean a BUFGMUX or a BUFG control primitive, and we'll talk more about those later. The BUFG was originally just an access point to low skew routing, but the BUFGMUX and the BUFG control have other features that we'll talk about later on. Access to all clock routing networks is provided by clock buffers. Now, global clock networks are driven by the global clock buffer called the BUFG. The regional clock networks are driven by a regional clock buffer called the BUFR, and the I/O clock networks are driven by the I/O clock buffer called the BUFIO. Now, the basic buffer primitive that we're seeing here has variations on the basic buffer and provides additional functionality, including switching, muxing, gating, and clock division functionalities. One variation of the global clock buffer, as we see here, is the BUFG control primitive. This buffer, the BUFGMUX, allows for glitchless switching between two different clock inputs. The timing diagram seen on the slide illustrates how this switching works. At first, S is high, so the buffer is driving the I1 input onto the output. At time T1, the select input goes low. If the buffer were to switch immediately, there might be a small glitch on the output. But to prevent this from happening, the buffer waits until the I1 input transitions from high to low. The BUFGMUX multiplexer utilizes the S port to implement a selection, so the S signal must meet the setup time requirements prior to the clock edge. Violating the setup time can result in a glitch, so check your FPGA user guide for more information about your device. The BUFG control behaves similarly, but there is no setup or hold time requirement on S to guarantee a glitchless switching, so again, check your user guide and see if your device supports the BUFG control primitive. The BUFG control primitive can be configured as a clock buffer with an input clock enable. This allows the clock to turn on and off dynamically, which saves dynamic power consumption. The behavior of this primitive is shown in the timing diagram on this slide. As you can see, when the clock enable port gets pulled low, the output is effectively deactivated. But for best results, the clock enable should be synchronous. The BUFG clock enable primitive must be instantiated and unfortunately cannot be inferred. Okay, let's now have a brief summary and then we'll wrap up part 1 of the Clocking Resources series of recorded e-learnings for the 7 Series products. In summary, each clock region has a height of 50 CLB rows and has 50 I/O pins associated with the bank, which is associated with each clock region. There are also 4 clock-capable input pins per bank, which can be configured as single-ended or differential inputs. There are 32 global clock buffers associated with the entire device. 12 global clocks can be associated per clock region, delivered via the BUFH, which is the horizontal clock buffer resource. There are 4 BUFIOs per I/O bank, 2 BUFRs, which are regional clock buffers per I/O bank, and 2 BUFMRs per I/O bank, which can drive multiple regions, hence the MR. There are 2 columns of clock management tiles per device, and they are adjacent to each set of I/O banks, which are on the left and right edge of the device. The clock management tile has 1 mixed mode clock manager, or MMCM, and 1 PLL. This module continues our discussion of the clock generation capabilities in the 7 series FPGAs. After completing this module, you'll be able to describe the clocking resources that are available in the 7 series FPGAs and specify some of the details about the clock management tile, that's the CMT. So again, this is part 2 of a series of 4 recorded e-learnings that discuss the clocking resources. Now specifically in this module, we're going to have a look at the clock networks and the buffers that are available to you, and then we'll get into the clock management tile. Now this slide shows a close-up view of a 7 series FPGA's clock regions. Each clock region is 50 CLB rows high and about half the width of the device. Each clock region contains 12 BUFH buffers. Now each BUFH can then drive any clock routing resource into that clock region, such as registers, shift registerlets, block RAMs, DSP slices, etc. Now you should also note that any 12 of the global buffers, that's the BUFGs, can drive the BUFH resources in each region. But basically, we're trying to describe to you that the global clock routing resources are segmented into BUFHs. Now, each BUFH drives its own horizontal clock routing resource into each clock region. Each clock region has 12 horizontal access points, or BUFHs. Each BUFH can take a clock input from a clock management tile in the same region, a BUFG, that's a global routing resource, or a clock-capable I/O pin from the same clock region. Now, the BUFH can also take its input from general interconnect for distributing a synchronous set, reset, or clock enable. Now, there's also a BUFH clock enable primitive with a clock enable input port, which is helpful for turning off a local clock into a region, which can help reduce your dynamic power consumption. Now, if you instantiate a BUFH or a BUFH clock enable in your design, an area constraint might be recommended to keep all the clock loads confined to a single clock region. Regional clock networks allow additional clocks to be distributed to the clocked elements within a clock region or area. And some regional clocks can also travel into neighboring clock regions. Regional clocks allow more clocks to be used in a single design as long as those clocks are not needed globally, but only among one or two neighboring clock regions. Regional clock networks reach the clock inputs of all the synchronous elements within that clock region. There are 4 regional clock networks per clock region, which are driven by the BUFR primitive. The BUFR can be driven by the clock-capable I/O pins, general interconnect for sets, resets, and clock enables, as well as the gigabit transceivers, the MMCMs, that's the clock management tiles, that are located in the same region, or by the BUFMR primitive, that's the multi-region BUFR. Now, BUFRs cannot directly drive regional clock networks into adjacent regions. This is accomplished with the use of the BUFMR. That's its purpose, is to drive multiple clock regions. The BUFR just drives one region. The BUFMR also has features for synchronizing multiple BUFR clocks. The BUFR can also divide an input clock by up to 8 for use in SerDes applications. And basically what we're talking about is distributing a clock locally into a single region when we use the BUFR. In every clock region there are 12 horizontal spines in the global clock network and 4 regional clocks. That makes a total of all 16 clocks. Now, all 16 can clock resources within that clock region, but only 12 of the 16 can enter the double column of CLBs in the top and bottom half of the clock region. So what this means is there are some limitations on which clocks can route to some of the CLBs in a clock region. Now, this should not be a problem since the tools will place logic into regions with this limitation in mind, so the tools will do the thinking for you. And in general, it is rare for a design to require more than 12 clocks into a single clock region. The I/O clock networks are designed to meet the strict timing requirements of high-speed I/O interfaces in terms of clock jitter, duty cycle, and insertion delay. An I/O clock network can only drive the I/O logic resources, that's the IOBs, in that clock region. Specifically, they are used most for double data rate and single data rate clocking of the IOB registers, as well as the iLogic and OLogic SerDes blocks associated with each I/O pin. Because the I/O clock network only drives a small number of elements, they are optimized for low fan-out, extremely low skew, and a very short insertion delay, which makes them ideal for source-synchronous interface applications. Now, these networks add the least jitter of all the clock networks and have run at the highest speeds, up to 1066 megahertz or gigahertz. The I/O clock networks are driven by the BUFIO primitive you see here. It can also be driven by clock-capable I/O pins most typically, but also can be driven by the MMCM outputs, the BUFMR, and general interconnect can also be used to drive the BUFIO primitive you see here as an input. In this example, we see a typical use of the SerDes resources. The BUFIO and the BUFR are placed in a clock region and have the same driver. The clock-capable I/O pins, now they are intended to be used together to create the 2 clocks. That's the high-speed and the low-speed clocks required for a SerDes component. This explains why the BUFR resources do clock division. The output of the BUFIO and the BUFR are guaranteed to be in phase, allowing proper clock crossing between clock and the clock div in the I-SerDes, O-SerDes components. Now please note all of this. The clock buffer, the networks, the regional driver, and the I-SerDes and O-SerDes resources are all in one clock region and in one column. Now this is how extremely high speeds can be achieved with the I/O resources in a Series 7 device. Now each bank has two BUFMRs. These allow you to take a clock signal from the BUFIO resources and allow it to span into neighboring clock regions. So they allow a single clock source to be driven to the BUFIO and to the BUFRs in the region above and below the source clock region. Now these are driven by multi-clock region clock-capable I/O pins that were labeled MRCC, as well as serial gigabit transceiver clocks that are derived from the dedicated serial gigabit transceivers. Now these can drive only the BUFIO and the BUFR buffers in the same clock region. That's the region again above and below as well. Now the BUFMR is designed to drive the BUFIO and BUFR primitives in multiple clock regions, again neighboring clock regions. Now this is necessary when building an interface that spans multiple clock regions, and that's more common now. Now these resources also have dedicated reset functionality to synchronize the BUFR resources. To do this, you must use the BUFMRCE clock enable primitive described and shown on this slide. In addition to the clock routing networks, the 7 series devices also contain dedicated high-performance clock connections for driving MMCM, or clock management tiles, generated clocks into the BUFIO, BUFR, and the SerDes resources. Now, these high-performance clock pads are designed to be isolated from the surrounding circuitry to reduce noise, which results in less jitter on the clock signal. And that's necessary in the case when we're driving our local I/O or SerDes resources with a clock-generated local clock management tile. Now, these performance pads are used when a clock signal is generated from the local CMT and drives a BUFIO, BUFR, or a SerDes resource in the same clock region. Now, the implementation tools will use these fast routing resources whenever necessary. The BUFG control and the BUFH primitives reside in the center column of the die, as we've discussed. The clock-capable I/O pins, BUFIO and BUFRs, reside in the I/O columns significantly further away. Now, the MMCM and the PLLs reside in the local clock management tile column, immediately adjacent to these I/O columns. And the serial gigabit transceivers, source clocks, are located further away on the periphery of the device in their own dedicated column. But the key thing here, shown on this slide, is that all these things are located apart, and there's dedicated routing paths that run between the H clock row to bring clocks between these resources. Now the tools, that's the implementation tools, will use these available routing resources when necessary. Now, in devices that are made up of multiple SLRs, that's super logic regions, recall that those are the largest density devices where multiple FPGAs are stacked together. There are still 32 vertical spines of the global clock routing resources for the entire FPGA system. Now, these spines traverse all the SLRs. Now, each SLR has 32 BUFG control components that can drive the vertical clock spines. However, only one BUFG control can drive any one clock spine, regardless of which SLR the BUFG control resides in. So what we're trying to say is that basically, again, even the larger density FPGAs still only have 32 global clock routing resources. So although there are n by 32 BUFG controls in the complete device, because recall there's n devices to build up one large FPGA, each die can be thought of as being its own device. In this case, however, on a large device that has superlogic regions, only 32 of the BUFG controls can be used. Because each SLR is a different die, its fabrication process can also vary from one die to another die. And this can mean there can be more skew than you might expect. Therefore, it is possible to see more skew on the global clock if it traverses multiple dies. Now, the implementation tools will automatically take into account this clock skew when verifying your timing paths when you use global timing constraints or path-specific constraints, and of course, instantiate the proper buffer. And this will be done by the tools automatically during the placement process when doing the timing analysis. However, to obtain the best performance, or if you have timing critical logic, it might not be a bad idea to use area constraints to restrict that logic onto a single die if possible. Now, this slide acts as a review for the entire module. Now, each clock region is 50 CLB rows tall. Each clock region has its corresponding I/O bank, and the I/O banks align perfectly with the clock region. So there are no I/O banks that cross multiple clock regions. There are 4 differential or single-ended clock-capable input pins per clock region. There are 4 regional clocks per clock region. The clock regions span nearly 1/2 of the die horizontally. You should also note that there are 50 I/O pins per I/O bank. There are 4 BUFIOs and 4 I/O clock networks per clock region. Finally, there are 12 horizontal clock spines, that's 12 BUFH primitives per clock region, and that means that most 12 global clocks can enter into a single clock region. Okay, so now let's have a short summary and we'll wrap up this recording. So besides the brief review we just did a moment ago about the actual physical resources that are associated with the clock regions and all, we want to mention a couple other things. First of all, don't start trying to control your design's routing. Even though we're giving this presentation as noted when the tools will automatically choose the appropriate routing resources, in general, it's not important for customers to understand how everything is routed on the device. It's very rare that they ever need to, but it is a good idea to understand the limitations. But be clear here, make sure you instantiate the appropriate primitives in your design when you want to get access to a particular resource. And that's kind of the point of us showing those primitives in some of the slides. You should also make certain you connect your SerDes clocks appropriately using the examples that we covered already and using the proper routing resources which are reflective of the proper primitive. Now, if you want to see other examples, you can check out the user guide and look for the Clocking Resources module in there, and you'll see some more examples. Now, you should also consider using area constraints to isolate logic into a single SLR, that's your super logic region, on your multiple die devices. If possible, this is useful when you're working with a device that has multiple SLRs and you have logic that's timing critical. So anytime you're doing that on a multiple SLR device, you might want to use an area constraint to keep that most timing critical logic on one die. Now note, stacked silicon devices still only have 12 global clocks on the entire FPGA device. Our objectives for this module are for you to be able to specify the resources that are available in the 7 Series' clock management tile, that's the CMT, and you should also be able, at the end of this recording, to be able to use the CMT resources into your design. So let's get into some of the details of the clock management tile. Now, each clock management tile has one MMCM and one PLL. Now, the 2 resources share some of the basic functionality, but the MMCM has some additional features for manipulating user clocks. Now, while the PLL can also be used for user clocks, it is primarily intended to be used in conjunction with the I/O phaser and the I/O FIFOs for high-speed memory controllers. Now, this CMTs perform frequency synthesis, clock deskew, and jitter filtering. Basically, everything in the PLL and the DCM have done from previous device families. Now, the MMCM accepts a very high input frequency range, anywhere from 10 to 800 megahertz. That's a very wide range and allows very flexible frequency synthesis. Also note that the VCO that's required as part of the PLL, the VCO frequency has been improved in the PLL to support up to 1.6 gigahertz. Customization of these components is done with the clocking wizard via the architecture wizard or core generator. And there are 2 kinds of primitives. There's the base primitive and the advanced primitive, which you can see on the slide. The advanced primitive will give you access to the advanced features and allows clock switching between 2 clocks without burning a BUFG mux. Now, this diagram shows the internals of the MMCM and helps explain how it works. The first portion of this diagram shows how the clock switching functionality is built in to allow synchronous switching of the source clocks. Then the output of that switcher is fed to a programmable counter divider denoted by the letter D. The derived clock is then fed to the phase frequency detector denoted by the characters PFD, which compares the feedback clock, that's the clock that has been selected to run back to the MMCM input, for clock input compensation. Now, the clock input detection circuitry is also found associated with the phase frequency detector, so we can determine if either the feedback clock or the actual input clock has stopped. The charge pump will adjust the output voltage higher or lower based on the feedback input to the phase frequency detector. The charge pump controls the VCO frequency, which, as I mentioned earlier, can be up to 1.6 gigahertz. This is then followed by the loop filter and the voltage-controlled oscillator again, or VCO. The oscillator has 8 programmable counters associated with it that allow our desired clocks to be generated. Now, many different output frequencies can be made based on a programmable multiplier and divisor value that you can set for each MMCM. Each MMCM can have its own programmable value, that is a multiplier, an M, a divisor, D, and an output, O, which is your multiplier, divisor, and your output, as I mentioned. Now, you can determine the range of these values they support from the Device Clocking Resources User Guide. Now, please note that as a division occurs, the duty cycle can vary, but the division will be correct. Static phase shift amounts can also be set independently on each MMCM output. And you can use the dynamic phase shift port, which will adjust the phase shift on all MMCM outputs, in addition to any static phase shift amount that is configured on each individual output port. So there's a lot of phase shifting functionality here as well. The PLL can perform frequency synthesis. The output frequency is actually defined by the M, the D, and the O values, the multiplier, divisor, and the output values. The M and D values can only be defined for the entire PLL, while the output value can be programmed for each of the 6 different output frequencies. The PLL can also phase shift all the output clocks independently and switch between 2 different input clocks. Finally, there's also dedicated cascade routing connections between the clock manager blocks that are in the same tile. This allows for greater frequency generation capability. Now, one of the nicest benefits is being able to configure the output O on an output basis. This allows you to generate multiple output frequencies from a single input. The MMCM also allows very fine phase shifting of 1/8 granularity. This enables a wider range of frequencies to be generated as well. Now, the MMCM also supports a dynamic phase shifting functionality, which allows you to actively phase shift the generated outputs based on a single input. The MMCM also supports cascading the outputs for a wider divider range. Outputs 0 through 3 also offer automatic complementary outputs at no extra charge. So if you need both the true and the complement output, you can have them without using any more logic. Now, active phase shifting is also easily accomplished with the phase shift clock, phase shift enable, and the phase shift increment decrement, and phase shift signals. A typical use of the PLL and the MMCM outputs is to drive the BUFG and the BUFH inputs for clock distribution. But outputs 0 through 3 can drive the BUFIO, the BUFR, and the SerDes clock ports in the same clock region. Clock insertion delay causes the most problems in I/O interfaces. That's because the clock to output times are increased because the clock delay path is in series with the data path. For inputs, the setup and hold time window can be extremely skewed, sometimes resulting in a negative setup time and very long positive hold time. Most I/O interfaces can't tolerate this type of time requirement, so something must be done to reduce or eliminate the large clock insertion delays. To that end, it's recommended that you connect one of the following ports as an input to the PLL and the MMCM clock ports, and that would specifically be the clock capable I/O in the same clock region, the clock capable in a vertically adjacent clock region, a BUFG, a BUFR, from the BUFH that is, but note that the gigabit transceiver clock would be good as well, but you must be careful with your use of the interconnect. That's not really recommended in this case. Now, these connections are among the most common use models, so it's strongly recommended you consider using them. And we'll talk more about the other use cases of the MMCM and the PLL in the next recording. But the other thing I'll point out to you as well is to keep in mind that these selections were made automatically for you when you configure your clocking resources using the core generator. And we'll look at that later on in the next recording as well. Now, the control loop of the PLL and the MMCM works to keep the clock in and clock feedback input ports in phase. This is regardless of the delay between the clock feedback out and the clock feedback in. So this is basically implementing a phase lock loop. So the compensation is dynamic. So even if the magnitude of the delay changes in time, the PLL will actively adjust to keep the 2 clocks in phase. The MMCM can also generate new clock frequencies based on the input clock frequency. The output clock frequency is typically measured as a fraction of the M divided by the divisor D times the input clock frequency. Now the range for the values of M and D can be programmed by the user with the use of the architecture wizard. That's via the core generator. But there are also some limits based on the device family. The MMCM or PLL ensures that the desired frequency ratio is exactly maintained. In other words, there will be precisely M output clocks for every D input clock. A feedback clock is not required, but it could be used to maintain a specific phase relationship to the input clock, which is sometimes essential. Providing this feature inside the FPGA reduces your overall system cost because external oscillators are not required to create the additional clock frequencies you might need. So with the PLL, there are 3 counter attributes to set: the output, the divisor, and the multiplier. Now, generally, you would want the phase frequency detector, that's the PFD, to be as high as possible within a valid range specified from the datasheet. To accomplish this, you simply make the divisor as small as possible. If the frequency of the VCO is high, you can generate more possible output frequencies, and you generally get better jitter performance. But a higher frequency of the VCO does consume more power. So if a large value of M is required to generate the maximum frequency for the VCO, the jitter can also increase. So to help customers determine what's right for their application, we've incorporated a jitter calculator as part of the MMCM in the customization from the core generator or architecture wizard. So when you go to the core generator to customize your clock, look for it when you get to that utility. Now the VCO generates 8 phase-shifted outputs, each shifted by 45 degrees. The interpolated fine phase shift, that's the IFPS module, generates a 9th output from the VCO, which can be shifted by any amount in increments of 1/56th of the VOC period. Now any of the 8 output dividers, including the M divider for the clock feedback out, can select any 8 of the static phase shifted VCO outputs or the fine phase shifted VCO output. So let's have a brief summary of what we've learned, and then you can listen to the 4th recording about usage models and how to use the clocking resources. So in summary, the PLL and the MMCMs offer a base for basic port functionality and advanced features, which include all functionality associated with this clocking component. Now the VCO is the voltage controlled oscillator. Ideally, the PFD should be as high as possible within the valid range for the device. If the frequency of the VCO is high, you can generate more output frequencies and you can generally get better jitter performance. But this is at the expense of increased power consumption. Now the MMCM also provides a fixed phase shift, interpolated phase shift, and active phase shift functionality as well. This module wraps up our discussion of the clock generation capabilities in the 7 series products. Our objectives for this module are for you to understand how to take the knowledge we've given you regarding the clocking resources and the clock management tile and be able to add them into your design in some very practical use models. So let's get into usage models, and then we'll talk about how to use and get access to the clocking resources. Bringing the clock into the FPGA through an IBUFG and then through a BUFG, which is your global routing resource, and then distributing it on that global clock tree introduces delay onto the clock path. Now this delay is process voltage temperature dependent and increases your setup and hold time window on your input flip-flops. It also increases your output valid uncertainty on your output flip-flops. So this restricts your high-speed interface design whenever you're routing your clock onto the global routing resources. So the key thing to understand here is the clock insertion delay will depend on the depth of that clock tree, which will increase your FPGA size. So obviously, the clock insertion delay has to be accounted for and possibly even compensated for to get efficient clock distribution. This example shows a basic circuit for removing the clock and insertion delays. The clock enters the FPGA on the dedicated clock input pin, indicated here by the use of an IBUFG input buffer. The clock then feeds into a PLL or MMCM, and the output is distributed on the global clock network using the BUFG primitive. Now the output of the BUFG is brought back into the PLL or the MMCM through the clock feedback input port, allowing it to adjust the output clock phase to match the input clock, thus the compensation of the input delay. Now the PLL or the MMCM effectively adds some delay to the feedback path to cancel out the delay of the IBUFG. Now this is done automatically by the implementation tools and by the device by setting the compensation attribute to Z-hold or zero hold. This will guarantee a zero hold or negative hold time requirement for all IOBs driven by the global clock. Note that both PLLs and MMCMs need time after configuration to align the feedback clock to the input clock. For details about the lock time required, see the datasheet for your device. By using the MMCM or PLL to remove the clock insertion delay, system components using a common clock can easily communicate with each other by using a simple synchronous interface. In this use model, we have multiple FPGAs all connected to a common clock. In this case, the clock is connected to an IBUFG, which is a dedicated clock pin, and routed to a PLL or MMCM. Likewise, the feedback of the distributor clock is fed to the same PLL or MMCM to compensate for the input delay on each FPGA. Now, by building your circuit in this way, the hold time requirements of the receiving flip-flops are guaranteed to be met, and communication can be done at moderate speeds over significant distances. You should also note that ideally the length of the board routing from the common clock to the IBUFG inputs in both FPGAs should be matched. You should also use the same type of input and output buffers on the data pads to balance the system. The PLLs and the DCMs in Xilinx devices have multiple clock outputs. Multiple clock signals that are generated by a single PLL or DCM has a known phase relationship. And since the delay through all global clock buffers and global clock networks is identical, these clock signals will maintain their phase relationships from the clock source all the way to their loads. All of this means that crossing between two clock domains can be accomplished synchronously and can be described with simple timing constraints. In fact, if a timing constraint is placed on the input clock to this PLL or DCM, the implementation tools will automatically analyze the timing requirements for signals that cross between the two output clock domains. Because all BUFGs are identical, the global clock networks are buffered, and the system is running at the same process, temperature, and voltage, the frequency and phase relationships of the PLL and MMCMs are preserved. Now, the implementation tools and the timing analysis tools understand these relationships correctly, and they correctly analyze the paths between flip-flops on these different clock domains. So, for example, if the clock output 0 is programmed to be twice the frequency of the clock feedback output, the implementation tools note that the static paths between the two clock domains are constrained by the period of the faster clock. Likewise, if the frequency is the same but the phase is shifted, that is, clock out 0 is advanced by 90 degrees from the clock feedback output, then the tools are also smart enough to constrain the data paths from clock A to clock B to 3/4 of a clock period. Now, likewise, the tools will constrain the paths from clock B to clock A in this situation to 1/4 of the clock period. Now, all of this discussion is to give you some comfort that the tools are smart enough to do some timing analysis that you might otherwise have forgotten when we are sourcing clocks from a single PLL or DCM. This example shows how a PLL or DCM in a Xilinx FPGA can be used to create a clock mirror. Now note that the feedback input to the PLL or DCM doesn't have to come from the global clock network. In this example, two identical output clocks are generated and both are in phase with the input clock. You should also keep in mind that the board routing delays for the two output clocks needs to be matched in order for all the clocks to be exactly in phase at the various loads for the system to work. For this example, the user would probably build this circuit with the architecture wizard or core generator and then select the compensation equal to external option. This example shows how a single MMCM can be used to generate multiple clocks required by your system. Now recall that the M in multiplier and D divisor values are applied at all output ports, which means that the VCO value has to be divided down at each port. Now, the benefit of using the MMCM to build this is that it saves you from purchasing extra clock components and reduces your overall system cost. Not to mention the advantage because you have a fixed number of MMCMs and PLLs in your device, and perhaps you don't want to waste another MMCM to generate one of the clock signals we could hear. So in this example, since we have 3 different clocks to generate, we probably want to use as high a VCO as possible, since this will give us the most flexibility. And in this case, we need one clock to be 533 megahertz. In this case, that is used for the I/O clock routing resources, which of course are the fastest. And that means that it's going to probably be distributed to the SerDes resources via the BUFIO or via the BUFR. Now you should also note that this clock is routed on the high performance paths, which are associated only with certain MMCM outputs. Next, we chose to use the fractional divider. Remember that there is only one per MMCM, and that's associated with the output 0 output. In this case, we divide the VCO frequency by 19.75 to get our 54 megahertz output. Now this clock is routed to one clock region, so it can be distributed with a BUFH primitive. But typically, if the design does not have too many global clocks, then a BUFG would be fine also. Recall that you have a limit of 32 global clocks you can distribute on the BUFG resources. Finally, the highest fan-out clock simply divides the VCO by 16, a simple integer value, and that means it can be generated by any of the output ports on the MMCM. It must be distributed on a BUFG since its logic has a highest fan-out and probably spans multiple clock regions, so there's no choice there. It has to be in a BUFG. And as you can quickly discern, that really the key decision to make was, what is that frequency we have to generate for the VCO? That determines what is possible with the MMCM. Now, I'll point out to you, this is easily built with the architecture wizard or the core generator, and in fact, when you go through and customize this component, the tool will automatically determine what that VCO frequency is ideal for your situation. Speaking of the core generator and the architecture wizard, now let's go ahead and take a few minutes and look at how we get a hold of some of these resources. PLLs and DCMs can only be inferred for the most simple distribution of a global clock signal. Things like multiplication, division, phase shifting, etc. require direct instantiation of the DCM or PLL in your HDL code. For this reason, we recommend that you instantiate your clocking resources, and that's all of them, with the help, of course, with the architecture wizard or the core generator, which is designed to help you customize these resources. Now, these wizards will customize and configure PLLs and DCMs by giving you GUIs to set the proper attributes and include support for driving the output clocks on the appropriate global buffers. Likewise, it also helps you configure advanced features such as clock division, the use of global buffers, clock feedback, etc. Basically everything we've talked about in these 4 recordings. And the beautiful thing is, of course, is the utility is designed not to allow you to set something that's not possible or not allowable with the architecture. So the side benefit here is it does all the error checking for you before you actually even construct your finished design. You'll have a very good idea that it should work. Now, all clocking resources can be directly instantiated into your RTL code. The simulation models exist for all these resources as well. So behavioral and timing simulations are fully supported. Now, refer to the Xilinx Libraries Guide for HDL designs to document, or use the language template for a bit more information about how to instantiate or more details about the library of components. The PLLs and the MMCMs have many inputs and outputs as well as many attributes. Optimal dividers for obtaining the desired characteristics may be hard to derive, so again, we've provided you the clocking wizard via the core generator to help with design construction. It's a GUI that simply allows you to make all the settings through a series of GUIs rather than memorizing all the different attributes or referring to a documentation manual. So as I just mentioned, the clocking wizard seen here is accessed from the core generator catalog under FPGA features and designed underneath the clocking folder. Now this is a simple screenshot of the wizard. The wizard provides customers with easy access to all the clock management features, and it performs all the necessary calculations and issues an error if an illegal configuration is requested, or even it will put in like a gray box if you can't assign something due to some other assignment you've made. Now, this simple table allows customers to enter their desired clock frequencies and phase relationships. The wizard calculates the required attributes, that is your multiplier, divisor, and your output values, to produce the necessary desired clock signals. The wizard even allows you to select the type of buffer for distribution of your clock signals. And the wizard will then produce an instantiation template and automatically associate it with your ISE project. Now, let's go wrap up the series of 4 clocking resources recordings we've listened to now with a short summary. The architecture wizard makes it easy for you to build and instantiate your clocking resources. It provides an instantiation template as well as a GUI for customization of your components. It also includes a jitter calculator and calculates your parameter values that are appropriate and prevents you from making assignments that are not possible. It also has application-specific instantiations, such as configurations of your DCM or PLL to build a clock mirror, a system-synchronous clocking resource, and even feedback options that are built right into it. So again, I want to encourage you to refer to that as your best way to optimize your clocking system for your application. Now, as I mentioned earlier, the user guide for clocking resources in the 7 series is your best technical resource with more detailed information on everything we've covered in these 4 recordings. There's also the Designing with 7 series families course, which is also very worthwhile. Again, you've been listening to the 7 series clocking resources recording learning, part 4. And again, my name is Frank Nelson. Thanks for your time and attention, and thanks for your business.